Alright, welcome to Vibrations and Waves. This is chapter 25. This is actually quite a long chapter. This is the beginning of Vibrations and Waves, and we're actually going to be sticking with, we're going to do Vibrations and Waves, we're going to do sound, we're going to do light, we're going to get into a little bit of diffraction and refraction, and then we're going to get into electric fields, electric forces, and stuff like that. Basically all the way to the end. We're covering all the rest of the areas of physics now. But it all starts here with waves, and it kind of carries with waves all the way to the end, because now we're talking about a lot of things that travel like a wave does. Vibration is a wiggle in time. Yes, it's a goofy definition, and since this is a regular class, this is kind of the definition we go with. It's basically something that's vibrating back and forth. Another word for vibrating you're going to hear a lot of times is oscillating. It's oscillating in time. A vibration cannot exist in one instant. It needs time to move back and forth. So you're going to have something moving back and forth in a given amount of time, and that's how we're going to look at a vibration. A wave, you can say then, is a wiggle in space and time. So whenever you have a vibration in a certain amount of time, we can call that then a wave. A wave cannot exist in one place. It must extend from one place to another, whether it be a guitar string or your sound waves or anything like that. It has to go from one place to the other. Light and sound are both forms of energy that must move through space as waves. And we're going to talk about, they're actually very different, light waves and sound waves, and they act differently in different things. And we're going to talk a lot more about light waves in a couple of chapters, but in the next chapter we're going to talk about sound waves and how they differ. So, vibrations of a pendulum. One of the first things we're going to talk about is a pendulum. You know what a pendulum is? You've seen a grandfather clock and the little thing that swings back and forth. Or I'll also show you in class. I'm going to swing my keys back and forth. I also did this when we talked about potential and kinetic energy. I drew my little thing, my pendulum that swung back and forth for the potential and kinetic energy changing between the two states. That's what we're talking about here with a pendulum. You tie a stone to a string and you have a simple pendulum. Galileo discovered that the time a pendulum takes to swing back and forth through small angles does not depend on the mass of the pendulum or on the distance through which it swings. It depends only on the length of the pendulum and the acceleration due to gravity. So we're going to talk about a period here, and we kind of talked about it last time when we talked about circular motion, that capital T. The period, the time it takes to swing through one full swing motion, that's the time of a back and forth swing. That is your period. And do we remember what the unit was for period? It's the second. In our formula here, it doesn't look that great, but it's that capital T, the period, is equal to 2 times pi times the square root. That L is the length of your pendulum. So the long, like if I've got my keys held in front of y'all like I do in class sometimes and swing it back and forth, that length of the string is the L there in just gravity, or 9.8 meters per second squared. A long pendulum has a longer period than a shorter one. So the longer the string, the longer it takes to swing back and forth. That's kind of common sense. The shorter string, the shorter time it's going to take to swing back and forth. Our legs act like pendulums. Long-legged people move with a longer stride with less frequency than short-legged people. I'm pretty short. To keep up with somebody who's tall, I have to move my feet more frequently than they do because my stride is shorter. Long-legged things. Let's talk about giraffes or horses or ostriches, things like that. And compared to short-legged things like dachshunds or hamsters or mice, things like this, they're going to have to have much longer strides to keep up with longer-legged people with more frequency. All right. Simple harmonic motion, the back and forth vibratory motion of a swinging pendulum. This is sometimes called oscillatory motion. When something's just sitting there swinging back and forth and swinging back and forth, that's simple harmonic motion. I'm going to draw a sine curve on the board when we meet on Tuesday morning. Don't forget that we're meeting on Tuesday morning this week. We're going to label all the parts of this. A sine curve is a pictorial representation of a wave. So basically, a sine curve, the one that goes up and down and up and down, and you'll see this in class. The crest is the high point on a wave. If you look in your book, this is also going to be diagrammed for you. Crest is the high point, where a trough is going to be the low point. So right now, get the definitions, so whenever I bring these up in class and draw this diagram for you, you'll see what it is. Amplitude is the distance from the midpoint to the crest or trough of a wave. So it's from the very middle to the top or the middle to the bottom. Wavelength, this is distance from the top of one crest to the top of the next crest, or the bottom of one trough to the bottom of the next trough. It's the distance basically from any two identical points in the wave as it travels through. That's your wavelength. Frequency is how often a vibration occurs, how often it will vibrate back and forth. Remember, what's frequency measured in? Hertz. It's measured in hertz. For a pendulum, it is the number of back and forth motions in a given amount of time. If a pendulum swings back and forth in 1 second, then you have 1 vibration per second, or 1 cycle per second, or 1 hertz. Hertz is the unit of frequency. 1 cycle per second is 1 hertz. We talked about that. High frequencies are measured in kilohertz or megahertz or gigahertz. So 1,000 hertz or 1,000,000 hertz, and it goes up from there. And we have different frequencies, like AM radio is going to be kilohertz. FM radio is megahertz. You can have like satellite radio, which could be gigahertz. And you have different frequencies that it's all based on. Oh, and I've got that written here. That radar and microwave ovens use gigahertz. And we have stuff that uses even higher hertz ranges now. The source of all waves is something that vibrates. Something that vibrates. So the frequency of the vibrating source and the frequency the wave it produces are the same. So when I'm talking, my voice box is producing sound. And that's vibrating at a certain frequency. And the waves that are produced by my vibrating voice box are the same frequency as what my voice box is vibrating at. They have to match. If the frequency is known, we can calculate the period for this. Frequency is 1 divided by the period. We did these before when we did circular motion. Or the period is 1 divided by the frequency. And that should look familiar to you because we've done this before. When energy is transferred by a wave from a vibration source to a distant receiver, there is no energy transfer of matter between the 2 points. The disturbance moves along the length of the string, not the parts of the string itself. So when I talk, my voice basically is vibrating the air molecules around me. And the vibration travels through those air molecules. It's not actually my voice that's traveling, it's the vibration of through the molecules that it's traveling through. Sound waves move between 330 to, this says 350, they can get up to about 380 in air depending on temperature, and they move 4 times as fast in water. So the closer the molecules are together, the faster sound will travel. To find wave speed, it's basically the wavelength times the frequency. Speed is the same for all waves. You don't hear the high notes before the low notes. They all travel at the same speed. And we're going to talk more about sound in the next chapter. Basically, the speed is equal to, that's a lambda, that's a Greek symbol lambda. That's going to be the wavelength in times the frequency. And frequency is in hertz. Alright, now we're going to talk about some types of wave. The first one is called a transverse wave. Whenever the motion of the medium, rope, wire, whatever's moving is at a right angle to the direction of the wave. Page 370 has a great picture of this. So transverse waves form right angles, and when I draw the sine wave, I'm going to talk about these. Waves in stretched strings of musical instruments and upon the surface of liquids are transverse. Radio waves and light waves are also transverse. These are key things to remember, some specific ones that I might ask about. Longitudinal waves are a different type of wave. These particles of the medium move back and forth in the same direction in which the wave travels. So, and I will show you examples of these in class when we meet on Tuesday. The particles move along the direction of the wave rather than at right angles, and again, page 379 has a great picture of this for you. Alright, interference. We're going to talk about a couple types of interference. Can 2 rocks occupy the same space at the same time? The answer to that question is no, they cannot. Well, more than one vibration or wave can exist at the same time in the same space. If you drop 2 rocks in the water, the waves produced by each rock can overlap and form an interference pattern. The waves can increase or decrease or be neutralized. The first one I want to talk about is called constructive interference, also known as reinforcement. When the crest of one wave overlaps the crest of another wave, their individual effects add together. Think about when people are playing musical instruments. If two people playing the same instrument and playing the same note, basically you get something that's known as constructive interference. They build on each other and sound louder than with just one of them together. So it sounds much more loud. And I'll draw reinforcement on the board on Tuesday. Like I said, we're going to have a lot to talk about. Destructive interference. This is also known as cancellation. When the crest of one wave matches the trough of another wave. This is like the Bose headphones, or the different headphones that will cancel the different sounds. You hit the button and it basically will produce a opposite frequency sound than what it actually hears. And I'll talk more about this in class tomorrow, but this is a multi-billion-dollar industry actually. And I'll draw cancellation out. Out of phase is when waves from two objects arrive out of step. They don't quite seem right. This happens with cancellation a lot of times. In phase is when waves arrive in step, so you get your reinforcement. Alright, standing waves. You're going to do a lab on Thursday. Oh no, actually you're going to probably do it Tuesday. Tie a rope to a wall in a stationary. You're going to work with the slinkies a little bit. You'll move a rope back and forth, and the wave hits the stationary object and bounces back. This is a stationary wave, to where it hits one end and bounces back the other way. The parts of the rope that remain stationary are called nodes, and I'll draw these again up on the board on Tuesday. Antinodes are the part of the rope that move or occur between nodes. Standing waves are caused by interference, one wave coming back towards the other wave and basically moving through the first wave. You can produce a variety of standing waves if you double the frequency. You're going to do this in the lab on Tuesday, where you're going to move the slinkies back and forth, and you're going to try and see how many little curves you can get in it. You can do it once where you have one big one, and you'll do it where you get two of them, and you'll do it where you get three of them, and so on and so forth. Alright, the Doppler effect. This is going to come into, we're going to start doing problems with these on Wednesday. I'm going to explain this to you more. Change in frequency due to the motion of the source, or it can be the motion of the object that hears it. The greater the speed of the source, the greater the Doppler effect. How many of you have been sitting in your car and you hear a siren coming up from behind you? Well, as it gets closer to you, it gets louder and louder and louder. As it goes away from you, it gets softer, softer, and softer. This is the Doppler effect, because as the sound's coming towards you, you're going to hear a higher frequency than you normally hear. As it goes away from you, you're going to hear a lower frequency than you normally hear. But are they actually changing the frequency in the car as it comes towards you? No. It's just because it's coming towards you and going away from you, it sounds differently. You hear a siren coming toward you. This is just what I was explaining. It sounds fainter and fainter. The wave crests hit with more frequency when coming toward you and less frequency when they pass by. Radar guns work the same way. They bounce off cars and read the frequency they bounce back at. So that's how some, well, it depends on the type of radar gun, but a lot of radar guns work this way. The Doppler effect also occurs with light. So you can get different types of light will do the same thing as what sound will. When a light source approaches, there is an increase in frequency. This is called a blue shift. This is an important one. When a light source approaches, there's an increase in frequency. So if it gets more and more frequent, you get what's called a blue shift. And as it passes by, you get what's called a red shift as it's going away from you. Stars that are spinning, all stars spin, and you can see them through some different I guess microscope and telescopes. You'll see one side is blue and one side is red. The one that's coming towards you will look blue, the one spinning away from you will look red. Distant galaxies also do this. Those that are going away from you will have a red shift. Those that are coming towards you will have a blue shift. There we go. The side of the star that spins towards us has a blue shift, and away from us is a red shift. Bow waves. Bow waves. When a plane breaks the sound barrier, it is in front of the sound. This is on page 384, and I'm going to show you a little video of breaking the sound barrier with these. When you go supersonic, you're traveling faster than sound. There's jets can do it, but there are a few commercial planes that can fly faster than sound, and I'll show you some video on that in class. The bow waves, they crest overlap at the edge, and the pattern by these overlapping crests is a V. If you take a look on page 385 in your book, they're going to show you this. And the thing is whenever you're in a plane that's going faster than sound, if you're in front of the engines, you will not hear the engines because you're traveling faster than the sound of the engine can, and it's not going to keep up with you. The shock wave is the overlapping spheres from a cone. So basically, the shock wave that's coming out from you breaking the sound barrier, and you'll see a video on this, and when they break the sound barrier, you can hear it. It's a very, very loud clap. A sonic boom. This happens when you break the sound barrier. When a plane breaks the sound barrier, you hear it goes supersonic, faster than sound. It's faster than around 350 meters per second.